Yeah, so we can get started. So I want to do, we've been talking about doing A/B testing. There's the behavior pile. There's all this stuff going on, and so I wanted to discuss approaches to this. And as I started to get into it, I realized that there was a lot of kind of fundamental review that I needed to freshen up on to make sure I was kind of had my head right on this. So I thought it'd be useful to just go through it. Um, so. Hopefully this isn't too much review, but if it is, we can speed through it.
Oh, shit.
So basically, what are you eating the wrong lunch?
Okay.
Did you eat? You ate like a totally different
Yeah.
lunch.
I feel like totally spaced out.
He left me a little though. That was nice of him.
Oh
Yeah,
my god.
No,
I was
Alright.
wondering what I ordered.
So when we talk about A/B testing, well, for most of this, we'll talk about a pretty, the kind of simple theoretical case. But so when we're going to talk about it here, we'll, consider a random experiment where there's some binary outcome, but there's all sorts of real world things that this corresponds to. I'll use an example of a coin flip, but like, in medicine, it's, did, if I've got a control group and a test group, did someone recover from a disease based on some treatment? Mostly in our world, we'll be carrying out things like, does a customer do a thing that we care about? Do they purchase a product? Things that when people use the term conversions. So we're going to assume that there's some true baseline probability of a positive outcome. And, that's the status quo. That's what's normal. And we're going to change something that we think is going to alter this baseline. We're going to introduce a new feature. We're going to change the color of some button or something. And we want to know if the thing we did had an impact.
So like changing to build C batteries is not really fit in this framework, or like did the battery go down?
So in this framework, there's a binary thing that we want to measure. So if it's like a person, if we have a definition of churning, like a person churned, right, and we have a definition, we can say that user churned, that user didn't. Then an A/B test of like, did changing build C battery decrease churn?
Okay.
That's a thing that we could measure in this framework.
Gotcha.
There's some, in our population, there are going to be some people that are successes, conversions, whatever you want to call a positive outcome. Some people are negative outcome, and we want to know if there's a difference between two groups that receive different treatments. So in general, we're going to run experiments, and when we use the terminology, people refer to, the original as the control or variant A, and the test as variant B. Often you think of the control as like, what is normal, and then B is what you've changed. You could also just change two things and compare them against each other, right? Really, you just want to know, like, are these two things different or are they the same? And the intuition is that if they're different enough, then we decide what we did had an effect. Otherwise, we just decide that it didn't. And all of the statistics around this are like, how do you know if they're different enough, right? Because these are random processes. So they're going to be different just because of noise. When are they different enough? So the simple example is, let's consider, two coins. I give you two coins. They have unknown probabilities of heads P1 and P2. They could be biased. They could be normal. You don't know. But what I tell you is one of the two things is true. Either they're identical, so if they're biased, they have the same bias. They're fair, they're both fair. Or one has a different bias than the other. So how do we know, how do we decide which hypothesis? Are these two coins the same or are they different? Well, we're going to experiment. We're going to flip them both, and we're going to see how different their outcomes are. So, I allow you n flips of each coin, 10, 100, whatever. You can observe some number of heads, M1 for coin 1, M2 for coin 2, and you're going to decide based on how many heads you see, are these different or not, right? And the intuition is like, if I gave you 3 flips, you get 2 heads and a tail on one, and 2 tails and a head on the other, you'd be like, what? I don't really know if they're different or not. If I gave you 1,000,000 flips of each, unless they were really, really, really similar, you would probably be able to tell that they were different.
Quick question.
Yes.
So for alternative hypothesis, it doesn't necessarily to be the complementary of null hypothesis?
It could be equal. So this is one subtlety that, like, whether you do a one-sided test or a two-sided test, like, do you care about whether both tails of the null? So essentially what you're going to do is, in all of these, and we'll get to this later, is you're going to reject the null.
Right.
and
but
so
then-
which side of the null you integrate on is going to depend if it's a one-sided or two-sided. So we could have written, the only difference would be if we said, and I think an example I have later, it's a two-sided test. If we said P1 not equal to P2, it would be a two-sided test where you have to integrate kind of both sides of the tail. Here we just said for simplicity only one side, but that was just to kind of have consistency with the examples I give
Okay.
here.
Yep.
The main thing that it'll affect is your false alarm rate, whether you have to split your false alarms between two tails or just one. It's a good question though. So, I mean, one thing to keep in mind here is that if we knew both distributions, then we could just do the optimal thing, right? If we knew P1 and P2, we would need to do this. But also, if we knew, a lot of times when you learn this stuff in school to start, you know P1 and P2, and you can draw distributions and you can integrate through these things. The problem is that we don't know these, so we need some other statistical test, some function of the data that gives us a distribution that we can get a number out of and a threshold to make a decision. So I'll go on here. I'm just going to review. There's a lot of terminology around this stuff. Some of it's stuff we're used to. Some of it is a little different if you haven't done like classical statistical testing theory before. But the basic approach for all these classical methods is always the same, which is you're going to determine some test statistic, which is some random variable that's a function of the heads that I observed, this M1 and M2, and it's also going to depend on N. Or we may let N grow very large and go to infinity. And what we want is when people play, when they did all this stuff, Fisher and all the guys back in the day, they wanted some statistic whose distribution given the null hypothesis is computable. So if they were the same, there's some way that I can massage the data and compute a thing that I know. And then if the data we observe puts us in the tails of the distribution, and we say this is too unlikely given the null, then we reject the null hypothesis and say, well, the other thing must have happened because they don't look the same. And this is where p-values come from. So when you hear about p-values, this is describing the tail probability of the sampling distribution given the null hypothesis. And so when people say, p less than 0.05, it's, there's less than a 5% chance that this data could have come under the null hypothesis, so I'm going to say that I'm going to reject it and choose the other thing. And so this is the classical approach to this. Often you'll see that people will summarize the data in what's called contingency tables. And then, so here you've got, on the left, coin number one, coin number two, and then the outcomes. There's M1 heads, M2 tails, or M1 heads for coin one, M2 for coin two, and then the complementary number of tails. And then if you do the row and column totals, a lot of times they'll compute statistics based on these totals. For example, is one way to get around not knowing exactly the probabilities. But at the end of the day, the statistical test is going to take this table, it's going to take the data, produce a p-value, which we're then going to threshold, often arbitrarily at 0.05, because that's kind of a convention, and there's all sorts of controversy and stuff that's emerged around that. So when it comes to errors, I mean, we're pretty familiar with this stuff, and a lot of this is very familiar to what we're used to, right? And all the driver ident stuff and everything else that we do. There's going to be four potential outcomes in this case. Either the alternate is true, something's really different. We choose the alternate, so that's what we're going to call it a true positive or correct detection. The null is true, and we actually choose that the null is true, which is true negative. And then we've got false positive and false negatives, which people called at some point type 1 and type 2 errors. It's not a great mnemonic, and a lot of people don't use it anymore.
It's not true, Progressive uses it.
Progressive uses it? Oh, man. It's like, are they like electrical engineers? Or I heard a lot of electrical engineering and control theory, a lot of people use type 1 and type 2. No. But I personally find false positive and false negative a little more
Sensible.
descriptive and easy to So the relationship of these to other things we care about. So the probabilities of these things occurring are false positive probability, false negative probability. These are typically represented in testing theory as alpha and beta. And so since we're going to reject the null when the probability is under a certain value, if we reject whenever p is less than alpha for a one-sided test, that's going to correspond to a false positive rate of alpha. And if it's a two-sided test, if we care about, in that case you had earlier, if we care about p1 being greater than or less than p2, just not the same, then you just divide alpha by 2 because you'd have to split that those false positives between the two sides of the tails. And if our false negative rate is beta, then correspondingly the probability of correct detection, which and what we do every day is recall, is going to be the power of the test. So if we do this a large number of times, that's when the empirical probabilities that we see correspond to the probabilities that they're talking about here. So if we have counts of true positives, true negatives, false positives, false negatives, this is when you can compute an empirical false alarm rate and an empirical correct detection rate. And the empirical correct detection rate will correspond to the recall that we're used to computing on a set. And precision is a thing that isn't really discussed in this literature at all. And the reason for that is because precision depends on prior probability. So we also have, in this whole mix, and this isn't a thing that is really discussed here, is a prior probability. There's going to be some amount of times, and if we observe, if we know truth and we observe a large number of trials, there's going to be some amount of time that H1 is true. Right. And traditional hypothesis testing doesn't really take this into account. And you can compute a relationship between, if you just run through these definitions and do a bunch of algebra, there's a relationship between false positive rate, the false negative rate, the precision, and the prior. Or in the stuff that we do, there's a relationship between precision, recall, false alarm rate, and the prior. And that means that here in this testing framework, if a test has fixed power and a fixed false positive rate, then as you change the prior, you change the precision of the test. And so this is when you hear people talk about p-values not really being representative of, you'll have all these scientific studies where people say, well, it was statistically significant. And then they look at the empirical, there was a good article in Nature about this stuff like 2 years ago or something last year. Like the empirical probabilities of these scientific studies being right don't always match up, and it's because understanding the prior probability of your experiment being true or not is kind of a hard thing to think about, right? Like if we made an experiment that there's a control group, and then in group B, we're going to go to every TMF user's house and kick them in the nuts, right? And see if they continue using the app. That's not, in theory, we would expect that to never increase retention, right? But if we went into this treating those priors as equal, then if we did that experiment enough times with a fixed false alarm rate, we might observe a success. It'd be interesting. So,
You have a small group
yeah, I lost the thread here.
You could do it 100 times, right? Yeah. If you want to see 5 successes.
So is there anything? So these are all. This is a lot of background. Most of us know most of this stuff. Kind of having it all in one place, I found was helpful to kind of get my head on right for the subsequent stuff. Is there anything else anyone wants to discuss here? Okay. So for classical tests, the kinds of things that people do, so one of the oldest is Fisher's exact test. So the way that this works is you observe under the null, those row and column totals that I showed you earlier, you can show that they follow a hypergeometric distribution. So this is a thing that you can compute, and you're able to just compute the probability and reject the null if the differences between what you tally along one dimension, what you tally along the other, differ too much for those things to have been generated by equivalent processes. And this is referred to as an exact test because it's computing the value precisely for the number of samples that you have. So it doesn't need to hold only when n is large. So people will often use this when sample sizes are very small and asymptotic tests don't hold. But you could use this for any size test. It's got a few issues. One is people argue about the fact that you're conditioning on the marginals. I don't fully understand the arguments that they make about that. One thing I do understand is that it can be conservative because the distribution can only take on discrete values. So if you want a certain level of significance, you may not be able to actually get that empirically given the constraints of n and the other things in your M1 and M2. So you might actually, be working at a lower significance level. But in general, this is the thing that, you could use. What's much more common is people will use a chi-squared test. So this is an asymptotic test where you compare the observed frequencies of your successes, so the actual fraction of heads and tails that I got, that M1 and M2. And the trick here is just that if the null were true, then you could, first of all, you could just compute the variance, right? If the null were true, I would know that the probabilities were the same, the variance would add. I can compute an estimate that pi hat of the probability of seeing the total number of heads for both groups. And then I could also compute the variance in that estimate. And then if I compute that test statistic, that z squared, which is the difference between the what I observe in each group, and normalize it by that variance, you can show that under the null this converges to a chi-squared. And so here again, you've turn the data into a thing that has a known distribution, and then you can compute the tail probability of this and reject it if the null exceeds the threshold. So getting back to our example, so we've got our null hypothesis, we've got our alternate, and assume we get to flip each coin 100 times. Let's look at some examples. So here, case one, let's assume the alternate hypothesis is true. You're going to get distributions that look like this. So we've got 40% chance for the one coin and 60% chance for the other. We're going to, you can just compute these distributions. They're binomials when n is large, so they look pretty in Gaussian. And then the sorts of things you do is you can actually just go in, so stats has all these tests. So like chi2 contingency is, you can just compute the contingency table. So if I saw, for instance, the mode, right, if I saw exactly 40 and exactly 60 heads, I could put this into the contingency table and then either reject H0 if p-val is less than whatever I care about or accept it. In this case, I get a nice low p-value, and I say, well, these two are clearly different. Similarly, if I got, some slightly more extreme value, I got a few more heads than I would expect from M1, a few less heads than I would expect from M2, and compute the contingency table. In this case, this is just above the significance threshold. So here I would incorrectly, if I observe this, these are plausible outcomes. If I observe this, I would actually say that these coins were the same, even though they're not in this case.
Does the fact that 43 and 57 add up to 100, is that relevant?
No, they're just numbers. Any pair of these, any particular pair of outcomes is going to give you a p-value.
I want to make sure I didn't
Yeah.
something.
And you could plot out, I did plot out, and I didn't find it particularly illustrative, but you could plot out just the two-dimensional space of all the p-values you would get and see kind of the horizon of what combinations would be valid and what ones wouldn't.
I'm sorry, did you already have this? How can we know what's the effect of having a greater number of trials?
So that's what I'll talk about next, which is how you actually pick n, because that's what we're usually interested in practice. That may be the next thing. So in the case when the null hypothesis is true, these distributions will be the same. And so, maybe I observe things that are very similar, and I'm confident that they're, here, these are very close. I'm going to accept the null because my chi-squared statistic is going to tell me that these look like they came from very similar distributions. But, if these were a little more extreme, this would be another case where I would, incorrectly reject the null even though they were the same. So this is what, will happen in practice. And often, as Bill mentioned, often what we're really interested in is we want to know how many, in this case with our coins, what we want to do is be prescriptive. We want to say, all right, we want our test, we want to have a certain confidence that we're right. We want to have a certain confidence that, if we see, if there's a real difference, that we can observe it. If there isn't a real difference, that we're not going to mistakenly detect it. And so how many flips do we need to reach a certain level of confidence? So the factors that will affect this are the things that we've talked about, the alpha, beta, P1, and P2. And the way that you think about this more in the prescriptive case is that there's going to be some baseline probability, right, the control. So how often does something interesting happen in this environment? How often do you get heads with these coin flips? Or how often does a person, convert, buy your product or whatever it is you're trying to measure as success? And then there's going to be some difference between P2 and P1. And you can think of this as the minimum observable difference. If they're very close, then it's going to be very hard to measure them. And as they get further apart, it'll be easier. So there's going to be some point where we say, well, this is the minimum difference that I'm willing to observe. Anything smaller than that, I might not see. But I want to see at least this difference. And then we'll prescribe a power and a false positive rate. So how often, if there is a real difference, how likely do we want to be to observe it? And if there isn't a difference, what is the chance that we will mistakenly think there is? So in practice, if we have a good guess at P1, so if it's the status quo in your product, and we know how often people convert, retain, whatever we're looking at, then we could say, well, if we want to increase it by a certain amount, then what is the n we need to measure that? And that's usually how these calculations go. So one formula, there's a bunch of ways to do this. One formula that a lot of people use is from this 1978 paper, Casagrande. I won't go through the derivation because I don't fully understand it, but basically there's a formula that gives you the desired sample size. There's some chi-squared correction factor that is their improvement over the last person who did this. So, but at the end of the day, you can put in those numbers and you get out an n. So, for an example here, if I I think that my baseline probability for the one coin is a 0.4, and I want to see if it's at least 0.6 or more different from that. If it was a 0.8, I would be pretty sure to catch it. But if it was a 0.4 and 0.5, I might not. But at least, 0.4 to 0.6 is the difference I'm interested in. And I want false positive and false negative rates of 5%. Then I can go through and just turn the crank on these calculations and get out an n. And here it tells me 149 is how many samples that I would get, I would need to be guaranteed an expectation to meet those criteria. So let's do a little more practical and scarier example. So let's assume we have 5% conversion on something we care about, like click through on some purchase page, or people taking their 10th trip, in our app, whatever it is. And we're going to introduce some feature that we think will change that by 3%, which it's only going from 5% to 5.15. But if you're thinking about purchases, right? Increasing your revenue by 3% with a single feature change is a lot, right? So this is the sort of thing that people are testing all the time. We want 95% power and 5% false alarm rate. So when we do this and we run through, we get that. So this tells us we need at least like 550,000 in each control and test, so like 1.1 million users to be able to measure that difference. So this is where this stuff gets hard. When you're trying to measure something that doesn't happen often, which is usually the thing you care about, because if it's rare, it's usually valuable. And when you're trying to change it, you usually can't change it much, because if you can change it a lot, then your business would be easier. But usually it's hard to change the thing you care the most about. So in that case, that's like the hardest case where A/B testing is the most value, and it's like you can get really
Or you
screwed.
could think of it as like, how can I prove I have a low false positive crash detection rate? You need lots of examples.
Yes.
Billion
So one thing you can do just to show that this stuff actually works is like you can actually just go through and empirically compute this, right? Like sometimes you're going to get lucky, sometimes you won't, but on average. So this is just an example of going through and saying if I had really that P1 and P2, I can go through and simulate actual outcomes for control and test when they're the same under the null, compute the contingency tables, make decisions, do the same thing when they're different, compute the contingency tables, make some decisions, and then compute how often I had false alarms and correct detections. And so you can see here, this is like 10,000 trials. You get, this is verifying that formula is giving us the right answer. Well, the combination of that formula and that test statistic is giving us the right answer. And you get a similar thing for the Fisher exact, although you do see, especially at lower sample sizes, you see some of that conservative where it will underestimate your empirical rates will be a little lower. So the question is, what if n is too big? So the main things influencing n are going to be how extreme your baseline is. So very rare things are going to make it hard to reach significance, and that's usually the things you care about. And then what's the difference between P1 and P2? So small differences are much harder to measure. So what can we do if n is too big to handle? Typically you're not going to mess with alpha and beta too much, although like a product manager is going to look at an A/B test and it's going to say like, well, significance is 0.06 and that's close to 0.05, so the test is successful. So that happens. But typically what we're going to want to do is adjust what we expect to get for P1 and P2. So in other words, say like, look, I want a bigger minimum measurable effect. So if it's a small effect, I'm not going to be able to measure it, but I'm only going to measure bigger effects. So I'll need fewer samples, but I will be blind to small changes, right? So that's one approach. Another approach is to try to increase P1 by measuring something that's more common. So if you're looking at a funnel and you've got, people get to your purchase page and they click through here and they click through here and eventually they complete the purchase, you might have to look further up the funnel and try to see changes there. And it's not going to tell you exactly how it influences your bottom line, but on the plus side, hopefully increasing things up the funnel is going to increase things downstream, and those things are going to be easier to measure. So those are some of the ways that you can try to handle this. But there's lots of practical issues with A/B testing, and this is where the art meets the science, because people love to do A/B testing, and they don't always do it right, and it's not always a good idea, and there's lots of technical issues with doing it right. So some of the things that I've come across are, sometimes it's hard to target the right group. So with email tests, you care about people, you want to test the difference between two calls to action. So you've got an email, and it's, you're going to have one thing that says, click here to download TrueMotion Family, and then another button that says, TrueMotion Family is the awesomest, click here, right? And you're going to send an email test to see which one's better. Like, people have to open those emails. So there's you're going to have a test and control, and you're going to have these huge pools, and there's going to be all this gating to get to the actual difference between the tests. And sometimes there'll be a question mark where, you'll have people that you want to know, let's say, what you care about is if people were, let's say you have some special program, right? So you're going to send out emails to two groups of people, and some of them will enter the program in the control, or in the test, and then in the control you send out an email, but there's no program and they don't actually go through and enter. So in that case, you don't know who are the people from the control that would have entered your program if it was available, right? Sometimes there's not a complementary thing in control. So there's like, you'll have kind of people that come in to test the actual assignment, and for control, there'll be like a question mark of like, well, if the treatment had been available, who would have taken it? Do you understand what I'm saying? It's a little subtle. Like when you need a user action to engage in the treatment and you can't make that action available to the control, then there's a question mark of who in the control group would have taken the treatment if it had been available. And so you have this latent variable that you kind of have to...
That's where a placebo might help.
Right, so sometimes it's hard to come up with a right placebo, right? But that's exactly right. Like in medical, the placebo is exactly dealing with that thing of like the selection bias of who would actually take the medication. And so a lot of times in our stuff, there isn't like a comparable analog to a placebo. There's so many ways you can screw up A/B tests, and people do it all the time. Unexpected variations between control and test. You think that you've made them exactly parallel, and then there's some subtle thing that differs between them. Because the test gets this feature and control gets this, but then you realize in your architecture, well, people that don't have this feature also don't see this other thing. So now you've compounded the test because there's dependencies between what you thought was the simple variation and other parts of your product that you wanted to keep constant. Some of that's just the reality of the fact that we have a complex software product that we're trying to make small changes in. Contamination between tests. So trying to make sure that people are only in one test at a time is hard, and you often quickly run out of users. When is it okay for them to be in multiple tests at one time? How do you ensure, if someone leaves and comes back, there's a lot of making sure that that people are, someone logs out and logs back in. Are they going to get into a different test group or get the test over again? Do we need to worry about that or not? Just assigning people to groups can be hard, right? If we think of in TrueMotion family, right? Should you partition people based on their families or as individuals? And it's going to depend on the test. If it's a thing that, all right, I come in the door and I get one treatment and my parent gets a different one, is it going to make our experiences incompatible? So now I have to do it by families, and does that mean I don't have enough families to do the test that I want to do? So it gets, even simple things like assigning people to groups can get complicated once you're in the throes of a product that has all these dependencies. And then organizationally, it's just a nightmare. People, especially outside of data science, I screw this stuff up and I know sort of what I'm doing. People outside will just abuse these. They'll, so multiple testing, a common thing is you put all this dev work in, you do all this stuff, you get some answers out and the test wasn't successful. And then, a PM comes back and says, well, what if instead of, looking at, conversions, you looked higher up the funnel, or you split it between men and women, you split the test a different way, did that, Now you're multiple testing. If you're just going to keep, this is p-hacking, right? This is what you see in science pages. Yeah, everywhere in science is if I just keep looking at the data different ways until I find something significant, I'm basically guaranteeing myself a false positive. People also do that temporally. You'll see where, if you're able to track this stuff with your analytics, you'll watch it and you're like, oh, was the test successful yet? Well, how about now? How about now? What wasn't? You said it would take a week and it wasn't. Let's run it another week and see if it becomes successful. So you're basically saying I'm going to run the test until I get the answer I want, So there's lots of ways that this stuff can go. And it's hard for an organization to put a lot of work into these, especially when you're starting out and these are cumbersome and hard to do and you don't have all the machinery to really do these in a quick, automated way. You can really go awry because you put all this work in, and then to come back and say, well, it wasn't statistically significant. Nobody, especially outside of data science, wants to hear that. Any other thoughts, comments here? I'm obviously very passionate about this.
I think
dealt with some of that stuff.
I think that whole point of we want to see something we're not seeing it. How can we look at it differently in order to see it? it's like a really serious tightrope, because there are sometimes, often the first wave you look at something, even if there is something significant in there, you're not going to see something.
Yeah.
And it's only just to give a concrete example, we're looking at breaks in phone usage.
Yeah.
Is there more hard breaks during phone usage periods? Well, first pass says no, and then maybe we raise the break threshold, and then maybe we only consider certain types of phone usage, and then we, maybe just at the very beginning of the phone usage periods. It's like, you feel like they think that there has to be some kind of relationship, and you can find something if you look hard enough, because you always will. But it's tough.
Yep. I agree, and I welcome any suggestions about the best ways to deal with this. Some of the things that are true, if we keep testing them and proving them over time, hopefully they will continue to be true. But you see science struggle with this all the time, where people still can't figure out if fucking coffee or alcohol or eggs or whatever is good for you or not. I don't know. And then there's this whole issue of just prior probabilities, that none of this machinery that I even talked about even deals with this. So, is there even any way for us to really know if a test is like a sure thing or like a total bomb? If it's guaranteed to fail, there's certainly been ideas that people have come up with that I'm like, that's guaranteed to fail. That, or guaranteed to be a success. Let's put a positive spin on it. But then that means if everyone in the organization really believed that, does that mean that, kind of a uniform prior is not the right thing, And at some point, should we even be testing it? If it's, if there's something that's so, we're convinced is so guaranteed to be successful or guaranteed to fail, why are we testing it then? Because the entire, if those beliefs are at all founded, the entire machinery is inconsistent with. At the very least, you should apply some of that expert knowledge, I think, in your false alarm rates, or how you evaluate the test. Because just blindly applying this 0.05 threshold doesn't really represent all the side information. But overall, you can spend a lot of time and effort trying to do this, especially if you want to measure really small changes in rare phenomena. And people do spend a lot of time and a lot of effort doing this. So some alternatives to traditional A/B testing. So there's multi-arm bandits are a thing that a lot of people are into. These, I'm sure you guys have talked about this. This is related to reinforcement learning, right? It's the simultaneous exploration and exploitation. But the basic idea is given a set of random experiments, how do I choose among them in order and quantity to maximize both my ability to learn and my ability to accumulate successes while I'm learning. So this is appropriate when you want to the quote is earn while you learn, be able to maximize my sales while I'm figuring out what's the best way to sell. And it's good. One of the things that's good is quickly exploiting short windows of opportunity. So one of the examples is when you're trying to optimize headlines for news, right? The shelf life on that stuff is so short that you need something that can figure out quickly what's effective. And maybe the subtleties of statistical significance aren't as valuable as getting a lot of clicks and figuring out which thing gets you the most clicks. But there's a lot of arguments back and forth about when this is right and when this is appropriate, when it's not. And when you search multi-arm bandit, these will the search results you'll get. Why it is not better than A/B testing. Why it is superior to A/B testing. So people can become a little religious about this stuff.
One year trick.
That guy Chris is a jerk out.
Let's post it on June 1st and then 2 days later.
Yeah. There's been feuds about this stuff, but I wanted to dig in more to this. Originally, when I started putting this talk together, it was these alternatives were things I wanted to talk more about, and then I realized I didn't have enough. I needed to refresh on the foundational stuff. One other one that I've dealt with a bit is, this traditional testing is fixed horizon. We basically say we're going to observe people for a week or whatever, or we're going to pick a fixed sample size, and there's not this kind of continuous streaming. In most mobile applications, you've got people coming in the door, new users, right? And you want to look continuously, but you can't for exactly the reasons that we just said. Of like, if you're constantly looking, then you're going to inflate your false positive rate. So there are approaches to controlling the false discovery rate using sequential measurements, and it essentially boils down to a sequential likelihood ratio test that will converge to the true false discovery rate over time. And this was, if you've heard of Optimizely, this is what their stats engine is built on. So using this, you can basically look continuously and stop the experiment when it's successful, and if it's not going to be successful, it will basically never converge, and you can never turn it off, or you'll give up and turn it off at some point. But there's not the same risk of looking at it every day. So it's
So it takes into account that you've looked at more data and adjust the threshold as even.
yeah. And another alternative is just not testing. So we don't always need to A/B test. We need to be very judicious about it. It requires engineering and data science resources. You have to design these tests. They have to implement them. There's product. There's UI. So the potential upside has to be there in terms of the save future effort of saying, like, this thing's a bad idea, we don't have to do it. Mitigating risk of, like, if we roll this thing out, it's going to hurt users and we're going to lose money, people. Those potential upsides have to outweigh the cost of developing, performing, and analyzing the test. I've seen people A/B test stuff that are, some feature that say, at Runkeeper we got, maybe 100 people a day on, and it's like, who cares? Just turn it on and see what happens. Like, who cares? You're not gonna lose these people. It's not. And also, if you talk to a product manager or something, and they're like, well, we're going to do this anyways. Like, why are you, if you're just going to do it anyways, then why test it? If you've already made up your mind, So it's figuring out, when is this really a thing that we need to know? And often people, once you have an A/B testing framework, you can do these things much more easily. And so, people will use them to basically, like, soft turn things on, right? And do we have some of this capability in our stuff? Does anybody know yet?
Turn things on.
Basically, to take,
People?
with Flip,
Yeah, that's
like Flipper has, but does it have sort of a ramping
You
or?
have an arbitrary key you can choose.
Okay, so we're starting to have some of this where it's common practice to
Per
just
environment.
No, that's one of the keys you can use.
Oh, it can be,
You can configure it by any arbitrary key.
so you can configure it by
By a list of ethnicities.
because like common practice would be like, oh, we've got a new build out. We're just going to we're going to switch people over slowly and make sure that nothing blows up. And you'll do it both for mitigating scaling and back end and architecture stuff, but also to make sure that there's not some hidden time bomb in there. So once we have lots of people on the platform, those are kind of responsible things to do, and you can use your existing A/B testing framework to do that.
I don't know, but that's on the server side, right? That's not on the device.
Yeah.
Whereas Firebase has turned out, I think,
Which is good.
more difficult, where it doesn't actually let us target people really accurately.
So anyways, that's all I had for background. I'd like to, in a future talk, go more into some of these alternatives and the stuff that we might want to do differently than just the plain old vanilla stuff. But these classical approaches are how, we'll be, stuff like this is how we'll be evaluating the progressive behavior pilot and things like that. So.
Is there a framework for this?
For us,
No. Is there a Python framework that implements this?
SciPy.stats
Okay.
and knowing stats. But I'll share the code for this. There's lots of online calculators. It's hard without. One of the things about this is, like, a lot of people do it without, I think, really understanding what they're doing. And I did that for a while, just kind of using the online calculators and things, and had no idea, like, what test statistic they were using and what they were actually calculating, and why, if I used one and I used a different one and they gave me two different numbers for n, they were different. So there's a lot of background that people don't really. It's one of the many reasons people do this wrong a